Hey guys, in this video I will discuss improper integrals and how to solve them. In terms of solving, improper integrals are mostly definite integrals, except that we add some steps at the beginning before solving the definite integral and at the end after solving the definite integral. So, before we begin, let us recall the fundamental theorem of calculus. Theorem states that if f is continuous on the closed interval AB, then for any antiderivative capital F of small f on the closed interval AB, we have the definite integral f of x dx from A to B equals f of b, or capital F of b, minus capital F of a. Now, if you recall how the definite integral was defined, you remember that our function f, small f, needs to be just defined on the closed interval AB. It doesn't have to be continuous. Okay, and then we do the limiting process. We get the limit of Riemann sum, and if the limit of Riemann sum exists, then we have the definite integral. So in our discussion here, we will focus on these two conditions. F is continuous on the closed interval AB. So here, we are assuming that our interval is closed, A, comma, B. And because you just have from the interval A, comma, B, it's bounded. We also look at the condition, continuity of the function on the closed interval AB. So your F must be continuous on the closed interval AB. So what if any of these assumptions above is not met? Meaning, what if the interval is not closed? We have the half-open interval, say like this, or the open interval that looks like this. The other half-open is something like this. Okay, so what if we have the not closed interval? Or what if we have the unbounded interval, a to plus infinity? Or we can also have open at a, and it goes to plus infinity. Or the other side, from negative infinity to b, including b. So these intervals, these are unbounded interval. These are unbounded intervals. They go to infinity, or they come from negative infinity. Now, continuity, well, it's possible that our function is not continuous on the given interval. It could be removable discontinuity, it could be jump discontinuity, but our main focus is what if we have an infinite discontinuity. Okay? Although we will consider the other types of discontinuities. Okay? So, jump discontinuity, removable discontinuity, or infinite discontinuity. So these integrals are called improper integrals. If any of the assumptions here is not met or are not met, or both of them are not met, then we have the improper integrals. Now, in our discussion, we will have two types of improper integrals, type 1 and type 2. The naming type 1 or type 2 varies from professor to professor or reference book to reference book or university to university or other factors, meaning that my type 1 may not be the same as the type 1 of other professors when they discuss this topic. My type 2 may not be the type 2 of the other universities when they discuss this. Okay? So it depends on who is discussing the topic. Now, let us start with my type 1. So consider the region bounded above by the graph of y equals 1 over x squared, below the x-axis over the interval 1, comma b. So this is 1 and then this is our b. So this blue graph that you see here, this is your y equals 1 over x squared. And we are interested with this region here. Okay? When we discuss definite integral, we introduced it using area under the curve. If you remember, the area now of this region will be equal to the integral from 1 up to b of dx over x squared. So, if we integrate this one and find the actual value, that will be equal to 1 minus 1 over b. So the area here is equal to 1 minus 1 over b. Hence, if we replace the b with 2, we have 1 minus 1 half. This is equal to 1 half. So this area that we see here is equal to 1 half. If we replace b equals 3, then we will have 1 minus 1 third. This is equal to 2 thirds. And if we replace b with 4, then you will get the area 3 over 4. So what if we consider the area from 1 until all the way there? All the way there. We define capital A of B to be the area of that region, and that A of B will be equal to this, the actual value. But this is in terms of your variable b. So if we want the area until all the way here, then this one here all the way is actually going to plus infinity. And that area, we calculate it to be equal to 1. But the question is, how do we actually get that 1? Well, we have found that a of b, this is equal to the integral from 1 up to b dx over x squared. This is 1 minus 1 over b. But this one, it goes there to plus infinity. Then that area will be or limit or area equals limit as b approaches infinity of the integral from 1 to b of dx over x squared. But we know that this one here is 1 minus 1 over b. So we take the limit as b approaches infinity. And as b approaches infinity, this expression here, it goes to 0 as b approaches infinity. And that's why we know that the area will be equal to 1, because this will approach to 0 and we will have just 1. So what we did here is actually the method in calculating improper integrals. And at this point, we see the additional steps. We have the definite integral here. And as I have mentioned, you will do something at the beginning before doing the definite integral. It's putting this limit. And at the end, after doing the definite integral, which is this one, calculating the limit. But the big chunk of the work is actually doing definite integral. That's why I said that improper integrals, it's mostly definite integrals. So let us formally define this improper integral. And like I said, this will be my type 1, and in other references or books or professors, this may not be their type 1. But anyway, suppose our function f is integrable on the closed interval a comma t for all t greater than or equal to a. So that's for all t greater than or equal to a. We define this here, integral of f of x dx from a to infinity. This is equal to the limit as t approaches infinity of the integral of f of x dx from a up to t. And note, by assumption, your f is integrable on the closed interval at. This will have an answer. So, after getting the answer for this definite integral, because it is integrable on that closed interval ab, you do your limiting process. This integral here, what you will get is something in terms of t. Could be a constant, but most of the time, it will be something in terms of t. So the improper integral from a to plus infinity of f of x dx, it will be equal to the limit as t approaches infinity of the integral from a to t of f of x dx. On the other side, suppose your f is integrable on the closed interval t comma b for all t less than or equal to b. We define this improper integral of f of x dx from negative infinity to b of the limit as t approaches negative infinity of the integral from t to b of f of x dx. So very much similar to this one, except that we are now looking at the interval negative infinity to b. So in here, it means that we are actually considering the interval a plus infinity, while for this one, we are considering the interval negative infinity to b. Or let's close this one here. And the third one is, so before the third one, I'll just say, if the corresponding limits above exists, meaning it's a finite number, because you will have to do your limiting process after calculating the definite integrals. So if the limit exists, we say that the improper integral is convergent. Okay? So if there is an actual answer for this, a number, a finite number, meaning the limit exists, then the improper integral is said to be convergent. Otherwise, we say that it is divergent if the limit does not exist. Then the improper integral is divergent. For the third definition is, what if we consider the interval from negative infinity to plus infinity? So this time, we are looking at the interval negative infinity to plus infinity. In order to do them, you have to separate them into two parts. You just choose an A, any number, and put it as a connection between the two integrals. So remember, you have your integral from A to B. You can write this as the integral from C to B plus integral from A to C. So it's the same thing. From negative infinity to plus infinity, you just choose a number, A, let's say A, and then you calculate both of them, and then you add the answers, if they exist. Take note of that, provided that the improper integrals on the right are convergent. If one of them, for example, this one, does not have an answer, then the whole thing will be divergent. Okay? So if at least one of them is divergent, then the whole thing will be divergent. So that is our type 1 improper integrals. So if we look at the example, we have the integral from 1 to plus infinity of 1 over x squared dx, that's equal to 1. You just have to remember this one here, the illustration that we did earlier. So if we try to write it using the definition, integral from 1 to plus infinity, 1 over x squared, this is equal to the limit as t approaches infinity from 1 up to t. Oops, I forgot the dx here. I'll just put the dx there. Dx over x squared. And then we do the definite integral here. Again, this is just a definite integral. So after doing the definite integral, you will have your limit as t approaches plus infinity of 1 minus 1 over t. But then, as t approaches plus infinity, 1 over t will go to 0, so this is equal to 1. Let us consider our next example. Determine whether the integral 1 over x dx from 1 to plus infinity is convergent or divergent. Determine whether this integral is convergent or divergent. So in here, we have 1 up to plus infinity of dx over x. This will be equal to the limit as t approaches plus infinity of the integral from 1 up to t dx over x. But we know that the integral of dx over x, that's ln. So this will be limit as t approaches infinity of ln absolute value of x evaluated x equals 1 up to x equals t. This one equals limit as t approaches infinity, fundamental theorem of calculus. This is ln absolute value of t minus ln of 1. Absolute value of 1 if you want. Of course, ln of 1, this is equal to 0. But as t approaches plus infinity, ln of t will go to plus infinity. So this will be equal to plus infinity. Therefore, since it does not have a limit, the integral from 1 up to infinity of dx over x is divergent. So again, we started with the problem, integral dx over x from 1 up to plus infinity. Then we put it into, we use the definition of improper integrals by putting this limit. So this is the step, the added step before doing the definite integral. So that's our definition. From this part until this part, it's your definite integral here. You calculate the definite integral until you end up with an answer for the definite integral. And then again, the additional step is by calculating the limit, which is equal to plus infinity. Okay? Next problem. Evaluate from negative infinity to 0 of x e to the x dx. So we have integral from negative infinity to 0 of x e to the x dx. By definition, this is equal to the limit as t approaches negative infinity of the integral from t up to 0 of x e to the x dx. Now, you can continue working on this by writing all the time this limit, but some would just, do the definite integral separately. So, for instance, aside, we have the integral from t to 0 of x e to the x dx. We can do integration by parts. U equals x, dv equals e to the x, du equals dx, v equals e to the x. So this will be x e to the x, that's uv, minus integral of v du e to the x dx. So this will be equal to x e to the x minus e to the x. And we evaluate this, by the way, from t to 0. Okay? So evaluated from t to 0. At 0, this will be what? 0 minus e to the 0. Minus quantity at t, you got t, e to the t, minus e to the t. Or you can write this as 0 minus e to the 0, that's minus 1, minus, for this part, we can factor out e to the t. So we will have your e to the t times t minus 1. So from here, we will have limit as t approaches negative infinity of negative 1 minus e to the t times t minus 1. Now, here, remember that the graph of e to the x is something like this. So as t approaches negative infinity, the function e to the t will go to 0. So this one will be 0 times, and of course, as t approaches infinity, t minus 1 is still infinity. This will be 0 times infinity. This is an indeterminate form. So you will need your L'Hopital's rules if you want to find the limit. For that, let us proceed it. If you don't remember, please review your L'Hopital's rules. But anyway, if we continue, we will have the limit as t approaches negative infinity of negative 1. What we're going to do is to put e to the t on the denominator so that we will have t minus 1 over e to the negative t. Now, if you look at this, as t approaches infinity, this will go to infinity. On the other hand, as t approaches negative infinity, sorry, this one, as t approaches negative infinity, this will go to negative infinity, but doesn't matter. Similarly for this one, that will go to negative infinity, but it's still 0 times infinity. Here, as t approaches negative infinity, we have negative t here, so you will have e to the positive infinity, which means the denominator is now infinity. Okay? So in here, we apply L'Hopital's rules on this part. So this will be equal to negative 1. The negative 1 is this one. It is not affected by your L'Hopital's rules. L'Hopital's rules, we are only applying it on this part. It's negative infinity over infinity, or infinity minus infinity. So here we apply L'Hopital's rules. We have the minus there, and we have the limit as t approaches negative infinity. In the numerator, derivative of t minus 1, that's just 1. On the denominator, derivative of e to the minus t, that's minus e to the minus t. We have here minus and minus, so it becomes plus. But anyway, this one here, as t approaches negative infinity, this one here is 1 over infinity. And 1 over infinity, in our case, that's equal to 0. Which means the final answer here will be negative 1. Okay? So notice how we use a lot of concepts here. We have the definite integral. We have the integration by parts. And we have the limiting process. And in the limiting process, we need to do L'Hopital's rules. So you might need a lot of techniques. So you have to really remember, since you are calculating limits, you have to remember your techniques from your Cal 1. Okay, let's move on. Suppose we have this, the integral from negative infinity to plus infinity of 1 over 1 plus x squared dx. So here, from negative infinity to plus infinity of dx over 1 plus x squared. if we are going to strictly follow our definition, we have to divide this into two parts. We'll just choose a number, real number. Particularly, let's just choose 0. So we will have the integral from negative infinity to plus infinity of dx over 1 plus x squared plus integral from 0 to plus infinity of dx over 1 plus x squared. So now we have two improper integrals here. If both of them are convergent, then this will be convergent and we will be able to find an answer. Well, if we can find the answers, the actual answers for this one. By definition, we will have here limit as t approaches, say, negative infinity of the integral from t to 0 of dx over 1 plus x squared plus, on the other side, you're going to use the definition in terms of limit, but since you are already using a t in here, use a different variable for this limit. So let me use r. R goes to plus infinity of the integral from 0 to r of dx over 1 plus x squared. Okay? So, doing the definite integral, well, 1 over 1 plus x squared, straightforward formula. I hope you remember that. That will be arctan of x evaluated from t to 0, and you take the limit as t approaches negative infinity, plus, similarly, we have the limit as r approaches positive infinity, or limit as r approaches positive infinity of arctan of x evaluated from 0 to r. For arctan, I hope you remember the values. If not, the graph of arctan is something like this. So we have an asymptote, a horizontal asymptote here at pi over 2, and here negative pi over 2. The graph is something like this. Something like this. Meaning, as your x goes to plus infinity, the arctangent will go to pi over 2. As x goes to minus infinity, the arctangent will go to negative pi over 2. But anyway, let us continue with this. Limit as t approaches negative infinity. Here we have arctan of 0 minus arctan of t plus limit as r approaches plus infinity of arctan of r minus arctan of 0. Arctan of 0, that's 0. Okay, you can check this graph. As t approaches negative infinity, arctan will go to negative pi over 2. So this will be equal to negative of negative pi over 2 plus the first negative, it's from this one here. Plus, as r approaches plus infinity, the the arctangent will go to positive pi over 2. So that will be pi over 2. So adding them together, we'll get pi. Negative of negative pi over 2, that's positive pi over 2. So pi over 2 plus pi over 2, that's equal to pi. So that is for this problem. Okay? But this one. And notice that we have to divide it into two parts. Okay? Now, you may ask, can we do something like this? Integral from negative infinity to plus infinity dx over 1 plus x squared. Can we do something like this? Limit as t approaches infinity of the integral from negative t to positive t dx over 1 plus x squared. It is possible, but with some warnings. In general, you cannot just do it, especially if your function has discontinuity. If your function is continuous all throughout the interval, there's no discontinuity, then you can possibly do something like this. If your function has discontinuity, then you might want to do this here. Otherwise, you might get a wrong answer if you do something like this for functions with discontinuity. So just a little warning. Now, for this one, for what values of p is the integral from 1 to plus infinity of dx over x to the p convergent? So we want to know when this integral is convergent. So to do this, well, let us look at the integral, the definite integral first. Anyway, if you do 1 to plus infinity, you want to integrate this dx over x to the p. This is equal to the limit as t approaches infinity of the integral from 1 up to t. And then in here, I will write this as x raised to negative p dx. So we want to know for which values of p this will have a limit. And at the same time, we will be able to know when this limit does not exist. First case, the easiest case, let us do that. If p equals 1, then we actually have the integral from 1 to minus infinity, 1 to plus infinity of dx over x. In one of our examples, we found that this is already divergent. Because this will be ln of absolute value of x, and then, you evaluate from 1 up to t. Then you pass to the limit as t approaches infinity. So we know that when p equals 1, this is divergent. So what we're going to do is, suppose p is not equal to 1. Let us look at the integral x to negative p dx. This will be x to negative p plus 1 over p plus 1 or negative p plus 1 plus arbitrary constant c. We look at this further. If p is less than 1, then 1 minus p will be greater than 0. But 1 minus p, this is just minus p plus 1, correct? This is this here. What does this mean? If p is less than 1, the exponent that we see here is positive, meaning the x here remains in the numerator. Okay? So, we will have the limit as t approaches plus infinity of what? T to the negative p plus 1 divided by negative p plus 1 minus 1 over minus p plus 1, doesn't matter. But since we are assuming p less than 1, minus p plus 1 is greater than 0, this t here is in the numerator because exponent is positive. So as t approaches infinity, this one here will just explode. This will be equal to positive infinity. Take note, denominator here is also positive. So this will go to plus infinity, denominator here is positive. So the answer will be plus infinity. What does that mean? When p is less than 1, this integral is also divergent. So here equals divergent p less than or equal to 1. What if p is greater than 1? If p is greater than 1, then 1 minus p, so we put this p to the other side, so it will be less than 0. So what does this mean? We have the limit as t approaches infinity of t to the minus 1 plus p over minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. Since minus p plus 1 or 1 minus p is less than 0, this is negative. Which means that we can rewrite this as the limit as t approaches plus infinity of 1 over minus p plus 1 t to the p minus 1. So we put this on the denominator, we negate this power. So it becomes p minus 1. So this one, or we have p minus 1 greater than 0. Minus 1 over minus p plus 1. So the exponent of t on the denominator is positive. So as t approaches infinity, this denominator will blow up, meaning this fraction here will just go to 0. And we have that 1 over negative p plus 1. Or simply, we can rewrite this as 1 over 1, or p, 1 over p minus 1. So we have an answer if p is greater than 1. So if we go back to this will be 1 over p minus 1, p, or if p is greater than 1. Meaning, this expression here, this integral here is convergent when p is greater than 1. And it is divergent when p is less than or equal to 1. Okay? So I am introducing this because when we discuss we discuss series, we will need that one. This is related to one of the types of series. We call them the P series, but we'll get there. So we have this conclusion. Now let us look at the second type, discontinuous function. So in here, there is a discontinuity at B, and particularly our discontinuity is actually unbounded function, meaning the function goes to plus infinity or minus infinity. So the same scenario, how do we find the area there if they exist? In order to do that, we can, start from A to K, where K is something that is less than B, and then we do the definite integral. And then we let our K approach B. So the definition would be, suppose F is continuous on this interval A, comma B, and is discontinuous at B. Take note of that, discontinuous, it doesn't have to be infinite discontinuity. It can be jump discontinuity or removable discontinuity. However, I don't know if you recall that if there is only a jump discontinuity or a removable discontinuity, and there's only finitely many of them, then the definite integral will then there will be an answer to your definite integral, or the function will be integrable. But formally, in order to do that, is via the improper integral. You take the limit. So in here, the integral of f of x dx from a to b, that will be equal to the limit as t approaches b from the left. Take note of that. T approaches b from the left. So you have from a to b. So in here, this is your a. Your b is somewhere here. So the t will come from the left side of b. Similarly, if we have this one, the function is continuous on this interval, open at a, close at b, and there is a discontinuity at a, then this time, we have a to b, in the interval open at A, close at B, and your t is somewhere here, this will go to A from the right. So the integral f of x dx from A to B will be equal to the limit as t approaches A from the right of the integral f of x dx from t to B. And of course, if the limits above exist, then we say that the integral is convergent. Otherwise, it is divergent. And if the discontinuity is in the middle, if f is discontinuous at C, where C is between A and B, then you have to separate them into two parts, from A to C, and then from C to B. If both are convergent, okay, if both are convergent, then the whole thing will be convergent. If at least one of them is divergent, either this one or this one, then the whole thing will be divergent. Right? So that is our type 2 integral, improper integral. And again, this may be type 1 of other references. This is an illustration of the discontinuity in the middle. So again, it shows, infinite discontinuity, but it can be jump or it can be whole or removable. Example here, we want to find the integral from negative 3 to 2 of dx over square root of x plus 3. So the interval is from negative 3 up to 2. But notice that on the denominator, you got x plus 3. Particularly when x is equal to negative 3, x plus 3 will be equal to 0. So, you will have 1 over 0 at x equals negative 3. The function is discontinuous at x equals negative 3. So for this one, integral from negative 3 to 2 of dx over square root of x plus 3, this will be equal to the limit as t approaches negative 3 from the right. Take note, this is your interval from negative 3 to positive 2. Your t will be coming from here, so it's from the right of negative 3. We now have the integral from t up to 2 of dx over square root of x plus 3. Then you can do your substitution rule. Let us just do that. Instead of doing aside, let us continue all the solutions all the way. So u equals x plus 3, dx equals, or du equals dx, du equals dx. So this one here will have limit as t approaches minus infinity. And look at this. When x is equal to t, your u becomes x plus or t plus 3. And by the way, this one is not negative infinity, it's just negative 3 from the right. So when x is equal to t, u becomes t plus 3. So t plus 3, when x equals 2, u becomes 2 plus 3, which is equal to 5. And then I'll write this as u raised to negative half du. So this will be equal to the limit as t approaches negative 3 from the right of u raised to half over half evaluated from t plus 3 up to 5. So this will be equal to the limit as t approaches minus 3 from the right of 2 square root of 5 minus 2 square root of t plus 3. And as t goes to negative 3 from the right, this will be equal to 0. And it is in the numerator, so you will just have 0. Take note your t is coming from the right of negative 3, so your t is actually greater than negative 3. So something that is greater than negative 3 plus 3, it is something that is positive. So this is well defined when t is bigger than negative 3. So in the end, the final answer here is 2 square root of 5. Okay? Next problem here, determine whether integral from 0 to pi over 2 of tangent x dx converges or diverges. So in here, if you recall the graph of tangent, this is tangent, not arctangent. It is tangent. There is an asymptote at pi over 2, and the graph would be something like this. We need from 0, so I'll just start from 0 there. So there's a discontinuity at pi over 2. So this integral 0 to pi over 2 of tangent of x dx, this will be equal to the limit as t approaches pi over 2 from the left. Integral from 0 to t tangent x dx. I hope you remember the integral of tangent x. So I'll just pull it here. Limit as t approaches pi over 2 from the left of secant of x. Oh, not secant, sorry, not secant. It's ln of secant. Ln absolute value of secant of x evaluated from 0 to t. This will be limit as t approaches pi over 2 from the left of ln absolute value of secant of t minus ln absolute value of secant of 0. Secant of 0, that's 1. That's 1 over cosine 0. So this part here is minus ln of 1. On the other hand, we have the limit of ln of secant t. The graph of secant t, what is the graph of secant t? So in here, let me just emphasize, this is y equals tangent of x. For the secant, we have something like this. You still have this asymptote at pi over 2. This is 1. The graph will be something like this. Remember cosine pi over 2 that is equal to 0. So 1 over cosine pi over 2 does not exist. In any case, so we have here y equals secant x. As x goes to, or as t goes to negative to pi over 2 from the left, this will go to positive infinity. So this will be equal to ln absolute value, ln absolute value of, plus infinity, but ln of plus infinity, that's just infinity. So this is plus infinity. And therefore, we conclude that the integral from 0 to pi over 2 of tangent x dx, this is divergent. Okay? Here, I will have another example. We have the integral from 0 to 3 of dx over x minus 2. If you are not careful enough, you will just do the integral here and you might be able to get a finite number. However, take note that this function here, it has discontinuity at 2, and 2 is inside the interval 0 to 3, which means you have to divide this into two parts. Integral from 0 to 3 of dx over x minus 2. This should be integral from 0 to 2 dx over x minus 2 plus integral from 2 to 3 of dx over x minus 2. Then we apply the definition. We write this as a definition. Limit as t approaches 2 from the left of the integral from 0 to t dx over x minus 2 plus limit as r approaches 2 from the right of integral from r up to 3 dx over x minus 2. So take note, from the left, from the right, you have to make sure you are putting them in the correct integral or limit. But the integral of dx over x minus 2, that's ln. So in here, we will have limit as t approaches 2 from the left of ln, absolute value of x minus 2, evaluated from 0 to t, plus limit as t approaches 2 from the right. Again, this is just ln absolute value of x minus 2, evaluated from r up to 3, or that we will have here limit as t approaches 2 from the left, ln absolute value t minus 2 minus ln of 2, 0 minus 2, that's minus 2. You take the absolute value, so you remove the negative, plus, wait a minute, in here, this should be r, excuse me. So we have limit r approaches 2 from the right, ln absolute value of 3 minus 2, that's ln of 1, minus ln of the absolute value of r minus 2. Now, if you see this one, if you look at this, your t goes to t from the left, for, your t goes to 2 from the left, t minus 2 will go to 0 from the left, actually, but there's an absolute value, which means that it's still going to 0 from the right. But if you recall the graph of the ln function, it goes something like this. So as t goes to, or as x goes to 0 from the right, your function goes to minus infinity. So this one will have here minus infinity, minus ln of 2. And it doesn't matter. Your minus ln of 2 doesn't matter because we already have minus infinity in here. And therefore, this one here is divergent. So, even without calculating this part here, your integral is already divergent. Therefore, integral from 0 to 3 dx over x minus 2, this one is divergent. Now, what if you calculated this? So plus, of course, ln of 1, it will go to, ln of 1 is equal to 0. So you will have here 0 minus the other one here. It's again ln of 0 from the right, which means that this one here will be negative of negative infinity, which is equal to plus infinity. You might argue that this minus infinity will just cancel this plus infinity. But that's not how this improper integral works. If the discontinuity is at the middle, then we need both integrals to converge so that the whole thing, the original improper integral, converges. I want to discuss this last theorem. We call it the comparison test for improper integrals. Suppose f and g are continuous with g of x less than or equal to f of x. And we assume that both of them are positive for x greater than or equal to a. If the integral of f of x from a to plus infinity is convergent, then the integral of g of x dx from a to plus infinity will also be convergent. If the integral of g of x dx from a to plus infinity is divergent, then the integral of f of x dx from a to plus infinity is also divergent. So how is this? If, we are integrating from a to plus infinity, this is your inequality. So you got 0 less than or equal to g of x less than or equal to f of x. You integrate it from a to plus infinity dx, integral from a to plus infinity dx. The inequality direction remains the same. The inequality will be preserved if you are integrating them on the same interval. So, what does this mean? Well, if you integrate 0, by the way, that's still 0. But what does this mean? The first one, if the integral of f of x dx is convergent. If the bigger one is convergent, then this will have an answer. Correct? This will have an answer. It's a finite number, which means this cannot blow up. This cannot blow up because it's always less than something that is finite. Take note, f and g are continuous. So if f and g are continuous, definite integrals on closed intervals exist. So this improper integral will also exist if this improper integral exists. If this is finite, this is also finite. For the second one, if this one here is divergent, this means that this will blow up because your g of x is positive, this is divergent, then it can only go to plus infinity. But since this is always bigger than this goes to plus infinity, there is nowhere to go for this one, but to positive infinity as well. So this will also be divergent. So if the bigger one is convergent, then the smaller one will also be convergent. If the smaller one is divergent, then the bigger one is also divergent. As a particular example, let us show that this is divergent from 0 to plus infinity. So in here, your interval is from 0 to plus infinity. Oops. Particularly, let us divide this into two parts, 0 to 1 and 1 to plus infinity. The integral from 0 to 1 of e to the minus x cubed dx, this is finite because your function is continuous on the closed interval. Okay? If your function is continuous on the closed interval, it will always have an integral. It is always integrable on that interval. That's one of the remarks when we discuss definite integrals. Our problem is this improper integral. Integral from 1 up to plus infinity. So e to the minus x cubed dx. To do this, we will do something like this. If x is greater than or equal to 1, let me just write it this way. If x is greater than or equal to 1, then x cubed will be greater than or equal to 1. Well, that is true. This is actually what we need. So scratch this one. scratch this one. If x is greater than or equal to 1, then this is what I actually want. Your x is less than or equal to x cubed. For example, 2 cubed is 8. So 2 is less than 8. This is true. This inequality is true when x is greater than or equal to 1. If your x is less than 1 but positive, then we have the reversed. We have the reversed here. So we need x greater than or equal to 1. So if I multiply this by negative 1, I will have negative x cubed. This will be less than or equal to negative x. This means that e to the negative x cubed, this will be less than or equal to negative, or less than or equal to e to the negative x. So what does this mean? So the integral from 1 up to plus infinity of e to the negative x cubed dx, this will be less than or equal to the integral from 1 up to plus infinity of e to the negative x dx. We calculate this. If this is convergent, then this will be convergent. Take note, this is always greater than 0. If this is divergent, we don't have any conclusion for this one. So we want this to be convergent. But that's easy. Integral from 1 up to infinity of e to the minus x dx, this is equal to the limit as t approaches plus infinity of the integral from 1 up to t, e to the minus x dx, but this will be equal to the limit as t approaches infinity of negative e to the minus x evaluated from 1 up to t. But notice, this will be limit as t approaches infinity of negative e to the minus t minus negative e to the minus 1. And as t approaches plus infinity, you get here e to the minus t, but e to the minus t as t approaches infinity, that will be equal to 0. So the final answer here is actually e to the minus 1. This one here will go to 0 as t approaches plus infinity. Which means that this is convergent. So integral from 1 up to plus infinity of e to the minus x dx is convergent. Hence, integral from 1 up to plus infinity of e to the minus x cubed dx is also convergent. I don't know the answer. We don't know how to do it yet at this level, but I know that it is convergent. That's the only problem. That is what the problem asks us. Show that this is convergent. This is a finite number because this is continuous on the closed interval 0, 1. But for the improper integral here, we can only show convergence. So this one is also convergent because of the comparison test for improper integrals. Okay, so I still have one example in here. You can do similar solution, and yep, you can do this when you have time. So thank you, and see you in our next class.